Now, I need to talk a little bit about the time history of metamorphism. And the takeaway point here is that a rock doesn't simply jump from surface conditions to a very elevated pressure and temperature point and jump instantly back to the surface. There is a path it takes. It takes a path going down and a path coming back to the surface. That path may encompass a variable length of time. It may go down quickly and come up slowly, or it may go down slowly, come up quickly. Those are issues that you need to determine through careful analysis. But let's just examine how this path would appear if you plotted it on a pressure-temperature set of axes. And I'll call this the time, pressure, temperature history. We start with a rock sitting at some pressure and temperature, and I've diagrammatically put my rock at this point on the diagram. At some point, due to plate tectonic interactions, that rock is carried down to a deeper point in the earth, a point at which it's gone to higher pressure and modestly higher temperature. This burial can continue carrying the rock to still deeper locations and still deeper locations. At some point, it reaches its maximum depth. And all through this progression going down, you could imagine that the minerals within the rock could equilibrate to the changing pressure temperature conditions. At this maximum depth point, it would potentially equilibrate to the assemblage of minerals associated with that pressure temperature point. Now, as it comes back up to the surface, it in fact may not begin to cool down immediately. In fact, it may get still hotter than it was at its deepest pressure point. And I illustrate that by moving over to this point, which is at a shallower depth, a lower pressure, but it is hotter than at the maximum depth point. This maximum temperature point is, in fact, the point at which metamorphism reaches its peak. So I changed the rock again, the color signifying a new assemblages of minerals within it. Now, from the maximum temperature point, it's coming back up. It can take a path of decreasing temperature and decreasing depth, as shown by a set of arrows. And each of these steps may encompass a variable length of time depending on the tectonic history in the area. Finally, that rock is brought back to the surface, and as I've shown it, it's carried up a record of the minerals that were stable at the peak of metamorphism. So the whole process of carrying the rock down, this path I've shown here in red, is the prograde process of metamorphism. From the peak of metamorphism back to the surface, we would call this the retrograde path of metamorphism. Now, the recovered rocks near the Earth's surface often record the highest temperatures during metamorphism. And, well, here's an interesting point. If you're recording the highest temperature, you may have erased the record of the highest pressure because the higher temperatures may have occurred at a shallower depth. Now, retrograde reactions, the reactions from peak of metamorphism down to the surface, involve increasingly lower temperatures. And as the temperature goes down, kinetic barriers become more important and reactions are inhibited. Thus, retrograde reactions are much less common than prograde reactions in metamorphism. So here's the bottom line, and here's the story for metamorphic petrology. Metamorphic petrology is used to determine the tectonic history of an area by studying the assemblages of minerals and textures in the rocks. By studying those assemblages, you can do geothermometry. That's telling the story of what the temperatures were at the time of metamorphism. You can also do geobarometry. That's determining the depths at the time the mineral assemblage formed. Both geothermometry and geobarometry involve a study of phase equilibrium. There is a unique set of phases that are in equilibrium at different pressure temperature points. Now you also need the time element in this story, the chronology, and you get the chronology by a detailed study of radioactive systems. The decay systems can be used to date events in metamorphism. All of these topics are covered in higher level Earth and Space Science courses. Here I've just given you an overview and kind of the flavor and the tools that are used in these kinds of studies.